Right, okay, let's get started. Good afternoon, everybody. I'm Flo Bullough, and I'm the Head of Policy and Engagement at the Geological Society. And welcome to this, the 8th lecture in our Year of Space lecture series, which is all about the geology of the icy moons. This lecture series is part of our 2021 Year of Space, which has been a fantastic success and learning exercise in learning all about the rocks of our solar system. We've been directing our gaze upwards this year beyond the Earth to examine rocks, dust, gas, and other matter across the universe to understand the formation and development of other planets and moons. We've had a fantastic programme of public lectures, outreach activities, and many more with conferences until the end of 2021. So please stay tuned to our social media channels and newsletters for more announcements about activities throughout the rest of the year. If you've enjoyed attending today's lecture or any of the other lectures in the run, take a look at our website to see the full programme and register for more. The next lecture we're having is on the 10th of November with Veronica Bray. She'll be looking at the geology of Pluto. Also want to give a special mention to our Spacescapes public exhibition that recently ended in the Burlington House courtyard. If you missed out and would like to explore the exhibition virtually, you're in luck as we recently launched a virtual tour on the exhibition webpage. And you can find that at our dedicated website of spacescapes.geolsoc.org.uk. We're going to pop the link in both the Zoom and the YouTube chat during the talk in case you didn't catch that. And so today I'd like to welcome Claire Cousins, who is a reader in Earth Sciences at the University of St Andrews and part of the panoramic camera team for the European Space Agency ExoMars rover mission. Claire's going to take us on a tour of the icy moons and their spectacular geology and some of the amazing and unexpected things that we can find on them. If you have any questions for Claire during the talk, we'll be doing a Q&A at the end of the session. So please do pop your questions in either the Zoom Q&A box, or if you're watching on YouTube, pop them in the chat box on the YouTube channel. We're also going to be running a few polls today. Apologies to those attending on YouTube, but you won't be able to participate in those. But on Zoom, please do go ahead and take the best guess at Claire's questions. So without further ado, I'd like to hand over to Claire, who's going to take us on a journey through the moon, through some of the moons of the solar system belonging to some of our largest planets. Thank you very much, Claire.
That's fab. Thank you so much, Flo, and thank you for the invite as well to speak to you all. And thank you so much for sharing your lunch hour with me as well. And hopefully I'll keep you entertained over your sandwiches or whatever else you may be eating at the moment. So yes, as Flo said, I wanted to basically take you through a bit of a tour through some of the icy moons in our solar system. They're quite different worlds to what we're often thinking about with other planets like Mars, for example, and they're quite alien and quite different, and they're also really interesting in terms of trying to understand whether or not there were environments or are environments elsewhere in the solar system that may be suitable for microbial life beyond Earth as well. So they're interesting, firstly, just from a purely geological standpoint, but they're also really interesting from a biology sort of point of view as well. So I just want to take you through what some of these worlds are like, what we know about them, and also very importantly, what we don't know and what we're hoping to find out in the future. So for this talk, I'm going to show you where we find these icy moons, talk a bit about what they actually are, how are they structured, what are they made of, also why are they interesting, what are the different varieties of different processes and environments that we can find on these worlds, and of course, when are we going to explore them next? When can we expect to see new data arriving from these very distant and faraway worlds? So, oops, there we go. So where do we actually find them? So what I've got on the screen here, this is just a really nice schematic of our own solar system. So you can see Earth here, just sort of hovering over here near the sun. And we sort of find our icy moons actually way far beyond this, out beyond the asteroid belt into the outer solar system. And this is essentially because of how our solar system has formed back when all the different elements and compounds were condensing and forming the planets and moons and other kind of rocky and icy bodies in our solar system. It was essentially cold enough in the outer solar system to have lots of ice forming. And this is why we see all of our icy moons kind of hanging out in the outer reaches of our solar system. So we don't typically, well, we won't find any icy moons within the interior of the asteroid belt closer towards the sun. They're all in the outer solar system. And they're typically all orbiting around the large gas giants, so Jupiter, Saturn, Uranus, and Neptune. And there's loads of them, and there's a whole variety of different worlds that we find within these different icy moons. So that kind of brings me on to my first Zoom poll, which I hope you participate in, because it's a very different place out in the outer solar system compared to our local neighborhood around Earth. And I'm curious to see what you will think in terms of how many moons Jupiter has. See lots of varied answers popping up already. Okay, so you're all pretty much on the right lines there. So Jupiter actually has loads of moons. Hopefully you'll be able to see that in a second, and Flo is going to share that poll. Oh, Flo, can you get rid of the poll from the screen because I can't see my slides?
It's done, sorry.
That's all right.
It should have gone now. Has it not gone?
No.
Okay.
We're all just so keen to see the results of my first poll. I mean, you're pretty much bang on the money. You know, as you can see on the slide, hopefully, that Jupiter actually has loads of moons. It has 79 moons. This is a very different kind of sort of situation to what we're familiar with, of course, with our own planet, with Earth. You know, we just have our one little moon orbiting around us. But within all of these different moons that we have around Jupiter, and also Saturn as well, Saturn also has a large number of moons as well. This is where we find a huge diversity of icy moon worlds, and that's what I want to take you through during this talk. Flo, I can still see it on my screen.
Yeah, are you able to close it? Apologies, because I've closed it a few times.
Oh, let me see. Okay, yeah, no, there we go. We've got rid of that now. Perfect. Okay, so if we look at the moons that are around Jupiter, as I mentioned, Jupiter has a large number of moons. Oops. Sorry, I'm having a few computer problems. There we go. So Jupiter, as I said, has 79 moons, and 4 of the largest ones, the so-called Galilean moons, you know, these are the 4 largest, and this is also where we find some of our really interesting icy moon worlds as well. So this is what they look like. So if we just focus on these 4 here, because, you know, it would take too long to go through all of the different moons that we find around Jupiter. We have some of these larger ones here. So we have Callisto, we have Ganymede, and then Europa, which is slightly smaller. And Europa is a moon I will take you through in a bit later in this talk. And also Io as well. And of these 4 Galileo moons, Io is kind of definitely not an icy moon. Io is a very different kind of moon. It's incredibly volcanically active. It has things like these huge lava lakes that we can see on the surface. It's kind of a bit of a hot kind of hell world, if you like. You know, so it's a very different sort of moon compared to the icy moons like Europa and Callisto and Ganymede. So already, even just within those 4 larger moons, we can see a huge diversity in the geology and the geological processes and environments that we find out here. So Saturn, as I mentioned, likewise has an enormous number of moons as well, has 82 moons. Not all of these will even be named. And many of these are also icy moons as well. So again, here's just a couple of examples of some of these that I've also got included on this graphic here. So we have Iapetus, we have Titan, and Titan is a moon I'll also go into a bit of detail on because it's a very weird and wonderful world, very different to many of the other places in our solar system. Tiny little Enceladus, which is kind of tiny but mighty. It's a very small moon. Its diameter is sort of about the size of Spain, so it's pretty small, but it has all sorts of really weird and wonderful things happening on it. And also the kind of famous sort of Death Star moon. So this is Mimas, and it just by pure coincidence just so happens to look a bit like the Death Star from Star Wars. So I have another Zoom poll question for you, which I'll figure out how to close this time. So this is a true or false question, and the statement is Earth the only place in the solar system that has liquid water? Okay, fab. So, yep, so most of you there are all totally correct. So that's actually false. Earth is not the only place in our solar system with liquid water, which is, it's kind of funny because we tend to think of Earth as being very unique, as being the sort of, blue planet, and it's kind of what it's famously known for, is having this huge body of water upon its surface. But Earth is not the only place with liquid water within our solar system. The icy moons also have liquid water as well. So this is kind of how they're structured. So, what we typically see with these different icy moons, and again, here is just a selection of different types that we find in our outer solar system around Jupiter and around Saturn, is that we have the same sort of basic structure for these different icy moons. In the larger ones, like Ganymede and also Europa as well, we have a sort of metal core, a bit like the Earth has, and then this is surrounded by a layer of rock. And then around this, we have some layers of either ice and water, so liquid water, or just ice around that rocky layer as well, particularly with some of these smaller moons. And what I want to talk to you a bit about as well is the importance of that ocean layer that actually sits either sandwiched between other ice layers or between an ice and a rock layer, and why that's important for understanding the habitability of these different environments. So this image that you can see up here on the screen, we've got the Earth here to scale, and this just gives you a sort of a frame of reference for thinking about the size of these icy moon worlds. So some of them are quite large, like Ganymede and Titan, but a lot of them are actually really quite small, as I mentioned, especially Enceladus, which is especially small. So this is the kind of basic structure of an icy moon as we kind of think of it. This is Europa, as I'm showing as an example. So we have our metallic core, we have our rocky interior, and then around this we have our global liquid water ocean, which then sits underneath an icy crust. So very different to the kind of worlds that we're familiar with in our own local neighborhood, our inner solar system environment, with Earth. But this is, if you could take a cross section through one of these icy moons, this is kind of what you would see. You have your crust, your icy layer at the top, liquid water ocean underneath, and then that's interacting with a rocky layer underneath that as well. So you can kind of think of these as sort of giant global oceans hanging out in the outer solar system. And that's, of course, why we're thinking about these environments in terms of whether or not they would be suitable for microbial life. And again, thinking back to our own planet and Earth as being a sort of blue planet and being a sort of a water world, Earth doesn't actually have that much water relative to its size in comparison to these icy moons. If you were to sort of gather up all the water that we have in the oceans and the lakes and seas and rivers and sort of form it all into one ball, that's kind of what you would have. That's what you can see here. So actually, water on our own planet is really quite a thin veneer around the surface that we're all kind of occupying. Whereas when we look at icy moons, the sort of the relative volume of water that we actually have here is liquid water is actually much bigger. So these really are sort of the true ocean worlds within our solar system, rather than, say, planet Earth. And as I mentioned a bit before already, we need to think about water and how water behaves to really understand these ocean world environments and whether or not they would be suitable for life. So I want to take you on a quick little detour just to think about water itself. So water is the most abundant compound in the universe, and it's also composed of hydrogen and oxygen, I'm sure you know this, which are the first and the third most abundant elements in the universe as well. So the fact that we have this sort of prevalence of ocean world environments and water environments out in our solar system is actually not particularly surprising. Water kind of is actually everywhere. It's not a so it's quite an abundant compound available for different environments to have it present there. So it's not a surprise that we have these ocean worlds out in the solar system. But how that water behaves, especially when it's frozen, is what we really need to consider when we think about these icy moons and how they're structured. So if we think about water and how it forms ice, this is where we then start to get into the kind of nitty-gritty of how these icy moons are structured. So I've got a kind of cartoon, what we call a phase diagram, just up here on the slide. And so this is showing you how water behaves in the different states that water can be in as a function of increasing temperature and increasing pressure. And we're all familiar with this. We all get to experience water vapor, liquid water and ice every day pretty much here on Earth. Earth sits at what we call the triple point, where we have these three main phases of water, all quite happily kind of coexisting and transitioning between those different states. So while we have ice at the poles, and we have liquid water oceans, and we have water vapor in the clouds. And this is something we also partake in as well, these phase changes. When we boil the kettle to make our cup of tea, we're turning liquid water into steam as well. So this is something which, hopefully we're all sort of fairly familiar with, but this is kind of the graphical representation of that process. What we see with icy moons, not only do we have incredibly low temperatures, it's very cold out in the outer solar system, but because these moons are quite large bodies, we're also increasing the pressure quite a lot as well as we go down into the icy moon from the crust down towards the core. And as that pressure increases, and sorry, I lost my voice recently, which is why I'm a bit husky. As the pressure increases, the ice actually changes into unusual kind of exotic forms of ice that we're not particularly familiar with here on Earth, simply because the pressures aren't high enough. And that's what you can see on this phase diagram here. So here we have kind of our normal type of ice that we're familiar with. So it's kind of got a six-fold symmetry. And that's why things like snowflakes will always have kind of 6 points to them. But, sorry, but when we get down to higher pressures that we find on icy moons, we also get a whole variety of different kind of flavors of high pressure ice, which have very unusual structural forms that are, again, we're not particularly familiar with here on Earth. This is what we typically see in the outer solar system. And these don't have particularly exciting names, they're just kind of called ice 2, ice 3, we've got ice 5 and ice 6 down here as well. But we do find them on these icy moon worlds, and they're really important for understanding how those moons are structured. So if we look at some examples, so this is Callisto, so this is one of the larger icy moons, and what we actually have, because of this moon size, we actually have 2 layers of ice. We have the outer icy shell, so ice 1, our kind of ice that we're all familiar with, and that's this ice here, just colored here in light blue on this diagram. Underneath this, we have a liquid water layer, which is our global ocean on Callisto. And then underneath this, before we get to the rocky layer, we have one of these weird high pressure forms of ice. In particular for Callisto, this is called ice 5. So again, I've just highlighted here on the diagram where this is. And this is because the pressures are just getting so great that even though you have this liquid water ocean, the pressure increases so much that then this liquid water actually then becomes ice again. In this one here, we have ice 5. So we actually have this ocean sandwiched between 2 different types of ice layers on these icy moons, like Callisto. And when we look at another large icy moon like Titan, we see a similar kind of thing. The pressures here are a bit higher, and so rather than this bottom ice layer being ice 5, is actually a more high pressure form of ice called ice 6. Again, with our kind of familiar type of ice just sitting here on the surface, and then this liquid water ocean sitting in between. And what we have here with these larger moons, Ganymede is also like this as well. We have these oceans which are called sealed oceans, and that's because they're sealed between these two different ice layers, sort of regular ice on the top and high pressure ice underneath. And this is in contrast to some of the smaller moons like Europa, which have a different situation. They don't have this high pressure ice layer. So we call these open oceans. And so what's really important about these is that this open ocean isn't sandwiched between two ice layers. In fact, this ocean can interact with the rocky interior underneath. And this is really important for understanding how habitable these oceans actually are, because you really want to have this interaction between water and rock to actually release lots of elements and compounds present within those rocks into the ocean environment. And, water in itself, yes, it's essential for life, but it's not the only ingredient that life requires. Life needs a whole variety of different elements and compounds in order to perform lots of kind of biochemical processes. And a lot of those elements and compounds can actually just come from rocks themselves. So having that interaction between the ocean and the rocks underneath is really crucial for these ocean worlds to actually be habitable. So even though, Callisto is a huge moon and Ganymede, they're huge moons, they have these huge global oceans. The fact that their oceans aren't interacting with rocks underneath means that these oceans aren't necessarily really very habitable for life, even though they're huge environments in themselves. So I want to take you through some of these icy moons in a bit more detail. So I'm not going to go through Ganymede and Callisto kind of for those reasons. And I want to take you through Europa, Enceladus and Titan. Also because these moons, we do know a bit about them from previous missions. They're really interesting and they're also quite different between each other as well. So if we start off with Enceladus, so as I mentioned before, Enceladus is a really small moon, its diameter about the size of Spain, but it's got an awful lot going on this little tiny world. So it was explored by the NASA Cassini space probe for about 10 years between 2005 and 2015. This is just an artist's impression here of the Cassini space probe that was visiting the Saturn system. And this, Cassini was an amazing mission. It discovered so many different things. But what it discovered at Enceladus was that rather than just being a kind of static, small little icy moon, kind of not up to much, it actually had these huge, really active plumes of material kind of spewing out from the south polar region of this moon. And, venting out at speed as well, about 800 miles per hour, hundreds of miles into space. So the small little moon was actually contributing quite significantly to the local environment around Saturn. And this is what they look like, these vents, these plumes that are coming out of the south polar region of Enceladus. This is one of the Cassini images that you can see here. And you can hopefully see very clearly these kind of jets of material coming out from the south polar region. And this is where they're coming from. So again, this is another spectacular image from Cassini. They're coming from these, I hope you can see the sort of slightly darker blue kind of striation features just along the south region here of the moon. These are called tiger stripes. And these are kind of these large tectonic features on the south polar region where these vents are coming from. And they kind of got their name from images like this. So they're actually a bit warmer than the surrounding surface. And I kind of use the term warmer, very relatively, maximum is about 116 degrees, minus 116 degrees Celsius. So still incredibly cold, but, relatively a lot warmer than the temperature of the surrounding icy surface. And this can be imaged again by the Cassini mission, these thermal anomalies which match up perfectly with these tiger stripe geological features that we see at the South Pole. So this is where we're having all this ocean material venting out from. And not only is it doing that, it's actually contributing to one of the rings around Saturn as well. So this is a really, really big discovery. And so this is Saturn's E ring. So rather than the kind of famous main rings around Saturn, this is a more sort of wispy outer ring that we have around Saturn. And it's actually being sourced from these plumes that are coming out of Enceladus. So this is what you can see here in this image. There's Enceladus sat in the middle of this E ring, and it's contributing all of this material and sort of ice and dust out into the solar system environment, forming that ring. And this is what it looks like. So this is, I think, in my view, one of the most spectacular images that Cassini sent back. This is an image of Saturn, and it's being backlit by the sun, which is why we then get this fabulous image of all of the rings around Saturn. And you can see this E-ring here. This is the outer sort of very wispy ring around Saturn, and that's where Enceladus is. So one thing that was really nice about this is that we could actually, Cassini could actually be sent through these plumes to analyze the chemistry of them. So this is not what this mission was designed to do. This mission discovered these plumes in the first place. But fortuitously, there were instruments on board this mission that could actually analyze the, the chemistry of these plumes, which will then tell us a bit about what the ocean is like underneath. So these are the two different instruments that we use to analyze the plumes, the cosmic dust analyzer, and also a gas spectrometer as well to analyze the chemistry of the different constituents within those plumes. So this is what was done. This probe was flown through these plumes to find out what they were. And this is what it found. These plumes contain water ice, unsurprisingly, but they also contain other things as well, and they all tell their own little story. So these plumes contain salts as well, so particularly chloride salts, so things like sodium chloride. This is, again, a salt we're all familiar with. This is just, regular table salt, and also some other minerals as well, like carbonate minerals. And there's gases present within these plumes, things like carbon dioxide, ammonia, hydrogen, methane. There's also very small sort of silica nanoparticles too, and also organic material as well within these plumes. And I'll just go through each of these to sort of tell you what these mean, what these results mean. So if we think about the fact that there's water ice there in combination with salt, that means that we do have this water rock interaction that I was just talking about. So we know that this ocean on Enceladus is actually interacting with a rocky layer underneath, dissolving lots of minerals within those rocks into the oceans, which is then producing these salts. We have these gases present as well, and this is really interesting in terms of thinking about the habitability of these oceans. These are all gases that can be used for microbial metabolism, so the way that the different types of microbes can produce energy, at least based on what we understand about microbes on Earth. So we have ingredients for life to actually get energy from. The fact that there's silica present within these plumes suggests that there's hydrothermal activity going on as well. So not only do we have water rock interaction, we actually have hot water rock interaction too. So hydrothermal activity deep within that ocean environment as well. And again, we know looking at hydrothermal systems on Earth, this is really good news for life. And again, we found these organics present within the plumes as well. This also suggests that we have the basic kind of organic building blocks available for different biological molecules as well. So this means nothing in the sense of like, oh, there's definitely life here, but what we do see is that, well, we do actually, we're starting to tick off the basic ingredients that we know life actually requires present within this extraterrestrial setting. And taken all together, basically the ocean on Enceladus is thought to be a soda ocean, so it's alkaline, it's got a pH of around 9 to 12, and there's places on Earth which are not too dissimilar to this. So this is a kind of artist representation of what's going on Enceladus, kind of putting this all together. We have this global subsurface ocean underneath an icy crust interacting with a rocky layer. There is perhaps hydrothermal activity going on as well, because we have this silica. This is a mineral which really will only form if we have a high temperature interaction between rock and water. And quite beautifully, all of that ocean material is then spewing forth out into space, kind of ready for people to analyze. But we still have a lot of questions about Enceladus. We want to understand, what kind of life can live in a cold, high pH kind of alkaline ocean. Are the sources of chemical energy here actually sufficient to support life? These are all questions that we need to find answers for. And in terms of exploration, if there was to be microbial life present within the ocean on Enceladus, would you actually get kind of bits and pieces of it, kind of organic remnants of that microbial life trapped in the icy grains that are then coming out of these plumes from Enceladus? So, we know a lot about Enceladus because of the Cassini mission, a lot more so than we do some of the other icy moons. So briefly, I want to take you through Europa and then also Titan. So here is Europa. This is not in the Saturnian system anymore. We're back to Jupiter. Europa was explored really quite a long time ago now. It was explored by the Galileo mission, which was at Jupiter from 1995 to 2003. And again, like Cassini, this mission revealed enormous amounts about our outer solar system and the worlds that it contains. Europa is really beautiful. When we look at these amazing images of the surface of Europa, we see things like this. We see these sort of crisscrossed, kind of very fractured, features on the outer shell of Europa. We see all this reddish material as well, some of which seems to be aligning with some of these tectonic features. And what we're sort of seeing here is it's actually quite a young surface. We don't see the whole surface covered in impact craters like we see on our own moon, for example. So there's clearly processes happening here, probably cryovolcanism, so the eruption of this sort of water ocean material from underneath through the icy crust out onto the surface. However, this is not something that's really been observed in the same way that we've seen it happen on Enceladus. All of this reddish material here, this is something which has been the subject of much debate within the community as to what it is. It's likely to be salt deposits, so again, salts coming up from the ocean material underneath, and it's thought to be red because those salts are then exposed to a really high radiation environment around Jupiter, which actually then changes the colors of those salts, and that's been done through experimental work to show that process happening. So, again, we're looking at a situation where we have an icy shell, ocean underneath, the ocean's probably salty. So at least we do have, some ingredients perhaps there that life might be able to use. And then it's, being erupted onto the surface to produce all of these incredible features. But, beyond that, we really don't know that much about Europa. So this is a kind of beautiful schematic put together by NASA to kind of idealize what might be going on Europa, but this is all hypothesis. We don't know for sure that these things are all happening. We know the surface environment is bombarded by radiation from Jupiter. We know that we have all this reddish kind of sort of salty material precipitated out between all the icy material of the crust. This is going to be brought up somehow through cryovolcanism, whether it's through fractures and vents, or whether it's a sort of more like an overturning process in the crust, we just don't know. And then underneath this, we again have this global ocean, which is something we are fairly sure about. But how that global ocean interacts with the crust underneath, the rocky crust, again, is it hydrothermal vents? Is it just a sort of very static cold water process? Again, we just don't know. These are all really big questions that we need to try and answer about Europa. There have been some sort of really interesting observations which sort of have hinted that we might have active cryovolcanic plumes on Europa like we have on Enceladus. So these are observations made by Earth-based telescopes. So you can see in this image here at the bottom, it's got a sort of a grayscale image of Europa just sort of superimposed on the top where that moon is, just for context. But these kind of bright greeny areas, this is where we see local eruptions of hydrogen and oxygen increases, which may suggest that we're having these transient cryovolcanic eruptions. But as you can see, it's sort of not really particularly definitive. It's just kind of hinting that this might be happening. So again, still lots to find out about Europa. And that's good because we actually have some missions which are heading to Europa over the next sort of decade or so. So both European Space Agency and NASA have missions flying here. So these are all just space probes, are not landing on the surface or anything, but they're still going to provide a wealth of data about this moon that we really don't know very much about. So ESA's mission Induce, the Jupiter Icy Moon Explorer, is launches next year, and it's going to be exploring not just Europa but Ganymede and Callisto as well. We have the NASA mission as well a few years later. This is Europa Clipper, and as the name suggests, this is really focusing on understanding Europa itself. So it's going to be doing lots of flybys, gathering lots of data about the nature of Europa and the surface material that it contains, and then of course what that tells us about the ocean underneath. And then in the distant future, this is more of a concept mission. This is something under development as well, as an actual landed mission to Europa to really analyze some of that material in detail. But that's probably a long way off. So lastly, I just want to take you to Titan. So, both Europa and Enceladus, it's a kind of a similar sort of system. We have, liquid water ocean interacting with a rocky crust covered in a layer of ice, potentially with material coming out onto the surface. Titan is a very different kind of world. Firstly, it's a lot bigger. It's one of these larger icy moons. So it has one of these sealed oceans that I mentioned earlier. So it probably doesn't have its liquid water ocean interacting with the crust underneath. However, the surface of Titan has a whole bunch of features and processes which make it really fascinating. And also you can see straight away, it looks very different. We don't actually see the icy crust of Titan. What we're seeing instead is a sort of world, this moon, which is enveloped in a really thick atmosphere. And that kind of makes it opaque to see what's going on the surface from our own, from our own eyes. So if we were to fly up towards Titan, this is kind of how we would see it. But we can look at Titan using different wavelengths to try and see through that thick atmosphere. So if we look at it in sort of false color images, so slightly different wavelengths that we can't see, we can start to peer through the atmosphere, peer through those clouds and try and see what's happening on the surface. And what we can see already is some variation at the surface in terms of possible geological features. And then if we look at Titan in the infrared, we can start to see even more. We can see these very sort of high albedo, brightly colored, sort of pinky colored areas up near the poles. And we have sort of these darker areas around the equatorial regions, and then these sort of brighter bluey regions here as well. So already we're starting to see that we have geological diversity on the surface of Titan. And that's important because if we see diversity of features, that means then that there's lots of different processes happening to produce them. And one of the big discoveries about Titan was made at the North Polar region, was when people were looking at Titan actually using radar, which is that there was these huge lakes on Titan. These are all sort of shown here. This is just a false color image of one of these radar images. And these lakes here are called mare, and you can just see them here, got different names. And they're huge. Here's the scale bar, about 500 kilometers. So these are kind of like the sort of Great Lakes, of North America. And they're all in this northern polar region of Titan. And these lakes are really interesting, and you can see lots of features which are quite familiar to us, these sort of dendritic waterways kind of feeding into these different lakes. But these lakes are not like the lakes that we have on Earth. On Earth, we think of our lakes being filled with liquid water, whereas on Titan, these lakes are actually filled with liquid methane, other hydrocarbons, because it's a very cold and distant world, very different to what we're familiar with. And Titan, this is why Titan's interesting, beyond just being an icy moon. It's this really organic, rich world. It's very unusual. So, it's got a very cold temperature at the surface. This means it lacks liquid water at the surface. What liquid water it does have is, hidden beneath in one of these sealed global oceans. But the atmosphere is so interesting, and it's also perhaps quite similar to what might have been on the early Earth, a few billions of years ago. So it's got this nitrogen-rich, thick atmosphere, like we do. We have a nitrogen-rich atmosphere. And rather than having a water cycle like we have on Earth, we actually have this liquid methane cycle because it's so cold. But it produces a lot of very similar features. And we're really lucky to actually have some on-the-ground data from Titan. So again, this is from quite a while ago. This is from 2005. As part of the Cassini mission, there was also a lander that was sent to Titan. This is a Huygens Lander, and it was sent through the atmosphere, down through on this parachute, landed on the surface of Titan, and it got some incredible data on the way down. But again, very tantalizing. Again, it just sort of raises lots of questions rather than really solves anything. So as this lander was coming down to land on the surface of Titan, this is kind of what it was seeing. It was taking images as it was coming down, and it sort of revealed a very similar landscape to what we might see on Earth. We can see things like shorelines. We've got these low relief hills, and we've got things like river channels crisscrossing the landscape. It was actually all quite familiar territory, except it's not liquid water carving out all of these landscape features. It's liquid hydrocarbons, things like methane. So a really alien world. When it landed, it sort of happened to land in this kind of dried up riverbed, and we can see again familiar features to us, things like these rounded cobbles within this riverbed. But rather than being rock, these are going to be rounded cobbles of ice. It's just a very different kind of system. And when we think about the atmosphere of Titan, this is when it gets all very complicated, and really we have no idea what's going on, but there are lots of weird chemical processes happening here, and again, some of these can tell us perhaps a bit about the Earth as well back in its earliest days. So this is just showing you a sort of cross-section through the atmosphere of Earth and Titan for comparison. Again, we have this nitrogen-rich atmosphere on both of these worlds, but then the sort of more minor constituents are obviously then quite different. You know, we have lots of oxygen here on Earth in our atmosphere. On Titan, there's lots of methane. The temperatures, of course, are very different. But what Titan has and what gives it its yellow hue, what we can't see with our own eyes through the surface of this atmosphere, is this photochemical smog that sort of forms partly way down through this atmosphere. And it's from this smog that's then, you know, forming lots of sort of rain, particulate rain, things like organic compounds, and raining down onto the surface of Titan. And there's all kinds of processes that are going on here. You know, some of them, again, like I mentioned, we just don't really know what's going on. Lots of complicated organic chemistry, but it's producing this organic haze around Titan, giving it that yellow color. And a lot of this chemistry is driven you know, by sunlight, but also by energetic particles from Saturn's magnetosphere itself, kind of driving lots of organic chemistry reactions in the upper atmosphere. Is producing larger organic compounds, and you know, then these sort of rain down onto the surface of Titan. And one thing that it produces, which is quite cool, these sort of large dunes that we see on Titan as well. This is a bit what they look like. So these are huge, you know, these are just these sort of ripples that you can see on the surface. This is the image of Titan, and this is just a close-up image here. And these are massive, you know, they're sort of, you know, 100 kilometers in width, you know, so they're really big dune systems, and they're thought to be produced by a lot of this organic material raining out of the atmosphere onto the surface. But again, you know, this is all just, you know, hypotheses into what's going on, how we can understand these observed features. And I mentioned that Titan, you know, this haze layer, this organic haze, this is something that we think existed on the early Earth, you know, sort of 3.5–4 billion years ago. And so Titan can actually serve to help us understand, you know, our own planet and our own planet's evolution from its earliest days, when we did have a very different kind of atmosphere to what we have today. So it's a kind of two-way thing. We can use the Earth to help us understand these very alien worlds, but likewise, these alien worlds give us sort of little windows into past processes that happened on Earth, you know, a long time ago. And we can see other comparisons with Earth and Titan as well, which I think these are just nice because they're just amazing images, and it's just interesting to see some of the same processes happening on Earth and somewhere as far away and as alien as Titan. So on the left here, this is just an image showing these polar clouds on Titan. These are these bright orange kind of wispy cloud features that we can see in the atmosphere of Titan. And these are very similar to the polar clouds that we will see here on Earth. Again, you know, on Titan, these are going to be hydrocarbon clouds, whereas on Earth, of course, you know, they're water clouds. But the actual processes, you know, and the sort of features that they produce are actually remarkably similar, even though the sort of chemistry of these worlds are very different. And of course, one of the big questions with Titan, given that it's so different, that it's covered in this, you know, liquid, you know, organic sort of you know, set of environments, liquid methane lakes and so forth, you know, is carbon-based life, you know, aka the life that we're familiar with, actually feasible on Titan? And that's something that we don't know the answer to yet. You know, we don't know if biomolecules that make up life would be stable in these kinds of environments, whether there'd be enough nutrients available, and whether or not there'd be the right chemistry available to fuel metabolism and energy production. And this is probably the one world in our solar system where life would actually have to be, you know, really completely different to what we're familiar with here on Earth. You know, when we're looking at places like Enceladus and Europa, you know, these are ultimately still water-based worlds, you know, liquid water worlds with water rock interaction and producing a very similar type of chemistry to places that we have here on Earth. So life would probably be quite similar if it was to ever exist there. On Titan, it's a very different kind of world. You know, it's very different chemistry, a very different set of processes. So this is somewhere where life would actually potentially be really quite different if it ever was to exist there. So that's kind of just food for thought. And there will be a mission going to Titan to find out more about this world in 2027. So this is called Dragonfly. It's a really cool mission just from an engineering perspective as well. It's sort of the first rotocopter mission. It's going to move, you know, the whole of its payload around Titan. It's making use of its dense atmosphere to be able to actually fly around. Planetary exploration is a long duration thing. So, you know, it launches in 2027, arrives about 2034. So it will be quite a while before we actually find out any more about Titan from this mission. But yeah, no, it'll be the first actual sort of vehicle out there in space exploring another world to actually fly its entire payload around to lots of different places. to analyze lots of different environments and materials. So that's a really exciting mission, which is coming up in the future. So it'll be there for just shy of 3 years. It's going to explore all of these weird features, like these organic dunes. It's going to explore the floors of impact craters, all these different environments that we've seen in some of these images. And especially it's going to use its instrumentation to study the chemistry of the organic compounds that we have on the surface. Are we going to see evidence of kind of prebiotic chemistry, so the kind of chemistry that ultimately led to life arising here on Earth? Are we going to see kind of examples of that playing out on Titan in this kind of early Earth sort of style scenario? So again, that will perhaps inform us about how life on our own planet actually came into existence in the first place as well. So lots of really exciting things to come out of that mission in the future. So just to kind of wrap up and just to kind of remind you, that these are just a few of the many moons that we have out in the outer solar system, whether they're just ice and rock, whether they have an actual ocean present as well. And there's a huge diversity of environments present within these different moon environments as well. They're all incredibly interesting and they will take a long time to explore, but every time we have a mission to somewhere, we always discover something really quite new and quite exciting. So kind of just watch this space and just keep your eye on what's coming up over the next few decades. So with that, I'll wrap up. I had one final poll question, now taking you through these different worlds, which is where you think we should next send a astrobiology mission to look for evidence of life. And that's just going to pop up, I think, there. There we go. Seeing lots of love for Europa at the moment. Okay, well, so it's always very interesting asking this question, I find, because it's almost quite a sort of fairly even split between the 3 different places. Europa, I think, is also one that really just fascinates so many people because we know so little about it. So, it's a good job that we actually do have some missions going there over the next couple of decades. But yes, they're all very interesting. Lots to discover. Brilliant. Okay, well, with that, I'll wrap up and I'll happily take any questions that you all have.
Hi, Claire. Thank you so much. What a fascinating lecture. The Icy Moons and Titan are just absolutely mind-boggling.
They really are very different. Yeah.
And don't worry, we've got lots and lots of questions that are all really, really interesting as well. I don't know the answers.
I promise I'll know the answers to all of
them. Okay, so a kick-off starter question we have is, what defines a body as being a moon as opposed to another sort of planetary body?
Oh, that's a good question. So I believe there is there's sort of a formal definition for this, which is what kind of kicked Pluto out of the sort of the planet club. But I think broadly with the moons, what we're seeing is that they're a satellite orbiting around a planet. So that's really going to be the main sort of defining feature of what's classed as a moon. And I think that's quite a broad description, and that's why we have so many different types of bodies out there which are classified as moons. Some of them are spherical and round, like our own moon, and look quite sort of moon-like. Others are kind of unusual, sort of irregular shaped satellites, which are a lot smaller. But ultimately they're all orbiting around one of the planets within our solar system.
Great, thank you. And so how do we know that some moons have a metal core and others have a rocky core? How do we go about knowing that?
Yeah, no, great question. And actually, likewise, how we know that there's a liquid water ocean as well present on places like Europa. This is basically to do with kind of gravity and how the moon kind of wobbles as it goes. If we take Europa as an example, how it as it goes around Jupiter, how it's kind of wobbling around, and this gravity data is what then, along with this is density data as well. This is what then sort of leads to this understanding of how that moon has to be structured in order to sort of match up with the data that's being observed. And that's always how science is done, right? You have your data, and then the data can't change. That's the defining feature. So that's then got to be something you've got to then figure out what that data is actually telling you. And you come up with different models of what will then fit that data. And for the icy moons that have oceans, that's the best fit, basically, which is why there's so much confidence that we do have this liquid water layer and things like a metal core, for example, to basically explain things like the gravity data and the density data.
Okay, great, fascinating. So Io, is Io the only body in the solar system with a lot of sulfur? And if so, why is that?
So yeah, so it's interesting. So Io, as you saw in that image, it's kind of bright yellow because it does have all of this sulfur kind of littered across its surface. But I don't think that necessarily Io is, I have no idea if Io is the most sulfur-rich body in our solar system. Sulfur is quite, it's everywhere. It's one of the most common elements within our universe. We find it cropping up all over the place. One of the ideas about Europa, for example, is that it actually has quite a sulfate-rich or sulfur-rich ocean. And we have a lot of sulfur here on Earth as well. I think with Io, just because it's so volcanically active, because it's constantly being kind of squeezed around by Jupiter, that's what's causing a lot of this heat to exist on Io and then produce other volcanism. So I think it's kind of, on the surface appearances, it looks like it's, a very sulfur-rich world, but we do find sulfur in other places as well. However, I don't know for sure if it's actually the most sulfurous place in the solar system.
Okay. We got a few questions about the different sorts of ice on Enceladus, I think that was.
Yeah.
So is ice one less dense than water? And do we know anything about the pressures that the other ice layers might form at? Can we infer that from the information we have?
Yeah, so our understanding of these different forms of ice essentially come from experiments done back here on Earth, where people have, squashed ice at different pressures and then are able to analyze that ice in the lab and see what its structure is. And that's what gives us these different forms of ice, ice 2, ice 3, and so forth. Yeah. So in terms of understanding how that translates to an icy moon sort of situation, because we know the size of these icy moons, we know their density, and when we have sort of our sort of intelligent assumptions about what those different layers are within an icy moon, that then tells us about what the pressure is going to be underneath a certain layer of water or rock or ice or whatever. And so we can then take that known pressure or calculated pressure present on an icy moon and then say, okay, well, that means that this phase of ice must be the one that's actually present.
Yeah, I mean, it's always really fascinating to me that you can do these experiments on Earth and apply them.
Oh, it's crazy. I mean, yeah.
It's amazing. So linked to that, someone has a question about why would there be liquid water sandwiched between two layers of ice? Why doesn't it just freeze?
Right, no, that's a really good question. So if we look at Europa, for example, so Europa is around Jupiter, and a bit like with Io as well, actually, is constantly being kind of, it's just being like sort of squashed and squeezed all the time, just by the gravitational pull of Jupiter. Jupiter is massive, and so it exerts a really strong gravitational pull on all of its moons. And just the way its orbit is as well, it's about a certain distance that it's what we call a resonance orbit, and so you get this like proper squeezing and squashing of Europa from its orbit around Jupiter, and that generates a lot of heat. And so that's one of the reasons why we have sort of a slightly higher heat flow on Europa as well. But yeah, I mean, the temperature of these liquid water layers, it's not like it's super warm or anything, we're just in the liquid water layer, some temperature range and pressure range. And so it's going to be about 2 degrees, 1 degree Celsius or something. Okay. So it's going to be very cold.
And so for those sealed oceans, would you expect them to be homogeneous or stratified? And if they were stratified, does that potentially create the redox conditions ideal for life?
That's a very cool question. Yeah, no, these are great. You guys should just
a good audience today.
This is awesome. Yeah, no, I think that's a really good question. So yeah, as we see in our own oceans on Earth, we have lots of different stratified layers, right? Based on salinity, temperature, and that drives all of our ocean currents and circulation and everything else. Yeah, it's a really interesting question to think, would we actually have this sort of stratification based on chemistry or temperature or whatever on icy moon oceans? And I think we probably would, depending on what other inputs that you actually had. So in the case of say Enceladus, for example, if we have, active hydrothermalism, which is a fairly high temperature process operating on the crust, then we'll have local regions of higher temperature water interacting with lower temperature water. So you'd have some kind of stratification there. On Europa, one thing that's really cool about Europa is that because you have a lot of radiation coming from Jupiter, that's actually kind of breaking up all the water molecules in that top icy shell, and that's releasing oxidants into the ocean, or could be releasing oxidants into the ocean underneath, just from the breakup of those water molecules into hydrogen and oxygen from that radiation. And so at the surface, in the sort of surface waters of that ocean, just near the ice layer, that's where perhaps you would see more oxidizing processes happening. So oxygen being available, for example, which then wouldn't perhaps make its way further down in the water column. So yeah, there probably is a lot of stratification going on, but we just have no idea what it might be right now.
Okay, so there's lots to find out. So there's a few questions now about the plumes and the loss of material off the surface. So one person asks, if Enceladus is ejecting plumes, then is it reducing in size over time due to the loss of material or not?
Ooh, interesting. I mean, I guess it probably is, in terms of it is losing material. However, it's, in terms of its relative volume, the amount it's losing is so small, it's probably making a very tiny difference. But I don't know how long it would have to be going on for in terms of it to have an observable difference in terms of its diminishing in size. But yeah, ultimately it is having material being taken away from it, if you like, sort of constantly.
And so, for Europa, which is also losing material, I think, could that be contributing to the production of rings around Jupiter, the material of that?
Not so much. I don't actually think there are any rings around Jupiter.
No, that's true. There aren't. They're around Saturn. But could it make a ring?
Like a trick question.
I should have screened that. That is a trick question. We have another similar question about materials. So. So is the exchange of material between the moons of any significance? So is any of the material from Io dropping into the orbit of Europa or Ganymede or any of the others, or are they all just completely separate?
Yeah, no, they are all kind of affecting each other, I think, within their own planetary systems. So with Europa, for example, that's orbiting around Jupiter. We also have Io as well. So there was a big argument or debate, about what the chemistry was of the European Ocean, whether it was sort of, chloride, sodium chloride salts, or whether it was sulfur. And the reason for that is because we see evidence for sulfate salts on the surface of Europa. And so the big question was, well, are these coming from underneath, are they from the ocean? Or is it actually sulfur coming from Io, which is then being implanted on the surface? So Europa kind of captures a lot of sort of the sulfurous material coming from Io, sort of ends up on the surface.
Oh, wow.
What's the chemistry of the ocean is on Europa itself. So again, that's a big question. Is this sulfur on Europa sort of exogenous and from Io, or is it actually endogenous from the oceans itself? Or it could be both. But yeah, Io is almost certainly influencing, at least in part, the chemistry that we see on the European surface.
Okay, and that word was endogenous.
Endogenous, yeah. It's exogenous and endogenous.
And then just one more little thing about the hydrothermal activity. Why is that focused at the poles? Do we know?
Oh, I don't know. That's a good question. I'm not too sure. There's all sorts of things to do with the nuances of how these different moons will have formed, and it could just be that in the same way that Earth isn't a homogeneous planet, we see lots of different processes happening all over the place, why we have certain tectonic features in certain places. I think it's just due to the sort of the natural sort of heterogeneous makeup of these moons. It just so happens to be that the South Polar region is where we see these plumes coming from, but I don't actually know the sort of definitive answer to that.
Okay, I've got a couple more on Enceladus and Europa before we move on to Titan. So one question here about saying, if they recall correctly, salty water can induce its own magnetic field. Can you please clarify on whether this process is happening on some of the moons, or your understanding of it?
Oh, I'm not too sure. Yeah, I'm not too sure about that. I mean, certainly around Europa, so the radiation environment because of the magnetosphere around Jupiter is huge. So I think anything that say like Europa might be generating itself, and certainly it's going to be, the magnetic fields that we do see around these icy moons are the ones which have a metal core at the beginning, in the same, in the middle, at the same way that Earth has its own magnetic field as well. So those moons with a metallic core in the middle, they do have an observable magnetic field themselves. But yeah, I'm not too sure about the others.
Okay, and then just a quick question on, the new missions that are going to do flybys to the icy moons. When are they due to arrive at their respective places?
Oh, I can't remember. I had it on my, let me just double check my slides.
I think
again. They do change. They change a little bit throughout time, depending on how the mission sort of engineering is progressing and stuff. But basically, they're always looking for a particular window to actually launch these things from. So with Europa, so JUICE, the ESA mission, that's due to launch in 22, so next year. And then Clipper, which is the NASA mission, that's launching a couple of years later in 24. I can't remember actually how long they're going to take to get there. It's quite a while. I do know that Clipper is getting there before JUICE, just because it's using a different type of propulsion technology. But I think it's, we're talking in the order of, I think, like sort of 6 or 7 years or something to actually get there.
It's a long
journey.
Okay, so just moving on to Titan and Triton. Do we know what the latest models are for Triton, and is there an expectation of tidal heating of the core?
Oh, I actually know nothing about Triton. I'm so sorry.
No, that's okay.
There's just so many ways to do that. Triton, again, a really interesting world, around Neptune. But I mean, actually, next week's talk, Veronica Bray, she will probably be able to answer that question. She sort of knows a lot more about the sort of the distant reaches of our solar system than I do. So maybe save that question for Veronica.
Okay, tune in for that one. Do we think that there could be life in the water or the liquid at the bottom of the lakes on Titan?
Well, this is a really big question, and this all hinges on our understanding of chemistry of life and how it would behave in a very different solvent. So, all life on Earth, we're all water-based, right? Whether we're looking at extremophile microorganisms, or ourselves, or any other type of life form in between. We all have exactly the same biochemistry. We're all made of the same basic stuff. And we all need water. Water is what all of our biomolecules will kind of operate in. On Titan, we're looking at a very different scenario. Whether or not there's any, in terms of liquid water on the surface of Titan, I think that's something that's still, that's something we still need to really understand. In terms, like you say, at the bottom of these lakes, for example, I think for the most part, they're probably just going to be hydrocarbon lakes. And so then we're looking at the kinds of weird biochemistry that would operate in an organic solvent, so, thinking about what you might put in your car, for example, thinking about that instead of water being the solvent. And that's where a lot of experimentation on Earth is going to really help us understand that. That's really in the realms of, proper organic chemistry and trying to think about what weird exotic biomolecules might be stable. But they may not be, it's been actually quite hard so far to find something which would, which could actually comprise what you would call a cell, and the different biochemical machinery that makes up that process.
I would love to know what a methane lake looks like. Be fascinating.
Yeah, I know. It's just a bit nuts to me to always kind of think of all of these environments being very different. It's probably quite horrible, to be honest.
Just lastly on Titan, you mentioned that Titan's atmosphere is thicker than Earth.
It's denser,
denser, sorry. So then how does this interrelate with its weaker gravity?
I don't know. I'm not too sure. I'm not sure about the gravity of Titan.
Harder questions. And then lastly, there's quite a few people who asked us about your phase diagram early on to ask why David Bowie and Queen were included. So I will let you explain that. So that was so rather than show, I was looking for different phase diagrams of ice, and I didn't want to show one that was all super complicated and full of a ton of stuff. There was not, a lot of them showed temperature in Kelvin. Most of us don't think about temperature in Kelvin, and all this kind of thing. So I thought I'd just show a cartoon one that was a bit more, sort of accessible. And on it you've got David Bowie and Queen, and it's because they had a song together that was called Under Pressure.
So that's to explain that.
Intense pressures at the bottom of that phase diagram.
Yes, exactly.
Exactly. Right. Well, thank you so much, Claire. What a joy.
Thank you so much for having me. Sorry for getting a bit confused about my Zoom at the very beginning.
The icy moons are just spectacular, so fascinating.
They are. I think that's it. Watch this space, basically. You know, I feel like a lot of the time I'm saying we don't know stuff, you know, but that's what also makes it exciting.
So everyone listening, keep an eye out for the future missions. Exactly. If you want to have a look at some of the icy moon images that we included in our Spacescapes exhibition, then just go to the link in the chat. Our next talk will be with Veronica Bray on Pluto, and she'll answer all the questions we've had today about how does Pluto keep warm or have any rocks or anything on the 10th of November. And big thanks to Claire, thanks to NG who sponsored the talk this time as well, and hope to see you all soon to learn more about the rocks of the solar system.
Thank you all very much for
Thank you. Thanks so much, everyone.